Thanks for coming. Welcome to Designing for Errors in a Kotlin-first SDK. When to throw, nullify, or return a result. I got 20 minutes and a bunch of slides, so I'm going to get started. Just a bit of background first. Who am I? I'm a Kotlin developer. I've been working for 3 years for the ArcGIS Maps for Kotlin team at Esri, and I help to contribute to the design of our Android GIS libraries. And if you don't know what that is, we do mapping and geospatial solutions in our SDK. We have decades of combined experience designing geospatial APIs for Android. And this year, we actually migrated from having a Java-based SDK to a Kotlin-first one. So this gave us a big opportunity to revisit our error propagation strategies. So just a little overview of the plan. We'll talk about why error design is important, what the Kotlin best practices are for error propagation, do a brief case study from our experience designing errors for our SDK, and then tie up some loose ends with suspend functions, properties, and constructors. All right, so why is error design important? Why can't we just throw exceptions? Well, our API needs to satisfy a wide variety of use cases, and in any API, errors are going to occur. So having clarity on how those errors are propagated is absolutely fundamental to good API design. And to do that, we need to establish clear patterns and adhere to platform standards. And all of this is really in the service of improving our API's usability. So if we have clarity like this, then users can anticipate errors before they occur and write code to prevent it. If they can't anticipate it, then at least it's going to be a lot easier to debug those errors if they have a lot of information available to them. And worst case scenario, they need to come and contact us and get us to help them solve their problem. And it's going to be easier for us to help them with that if we design good errors. Why can't we just tell our users to catch exceptions? In Java, maybe it was more normal and acceptable to catch exceptions right there at the function call. But in Kotlin, it's considered a code smell. And really, if you think about a functional programming style where you're chaining method calls together, you don't want to have to insert a try-catch block around one of those function calls and completely break the flow of your code. So maybe it's OK to throw exceptions, but we don't want to force our users to catch them. All right, so let's go over some of the Kotlin best practices on how you should be thinking about errors. So we identified 3 types of errors. These are logic errors, domain-specific errors, and lenient errors. And I'm going to go over each of them now. So logic errors, the easiest ones, we consider them to be preventable at implementation time, meaning that the user can write code to make sure that the error doesn't occur at runtime. And they're unrecoverable at runtime. So if they do happen at runtime, basically that's not a scenario we want to occur. You can think about this as like an index that is taken as a parameter to a function, and the user passes in -1, right? This error should never happen. The code should have been written differently. How do we propagate these? This is the case where in Kotlin we throw an exception. And it's important to dock it with @throws, because the compiler is not going to tell them what that exception is or that your function is going to throw an exception. So they need to know about it ahead of time. The user expects that the exception is going to cause a crash or is going to lead to an application or subsystem restart if, for example, some higher level error handler is being used. And the user expects that this error is avoidable if they can check some documented precondition. So here's an example from our API. We have a 3D scene view, which lets the user visualize 3D maps. And the scene view has a camera, and you can move that camera to a point. And a point in our API has an x and y coordinate, and if either of those things are null or not a number, then we consider that to be an empty point. So this function, if you pass in an empty point, then the camera can't move to it, and it's going to throw an exception. You can see that here, the user is going to get some points of interest collection that they have, and they're going to try to call their camera.moveTo to that location, and their app's going to crash. So how do we prevent this from happening? Well, really, we just dock it with @throws. We tell them that it'll throw an illegal argument exception if the location is empty, and then the user says, OK, well, I might have an empty location, I might not. I'm going to first filter out any empty locations from my collection before I try to move the camera to it. And of course, first can also throw, but for the purposes of this example, we won't consider that. OK, the second type of error that we have are domain-specific errors. These are errors that are specific at implementation time, meaning that we know what the error is going to be and how it can occur. But they're recoverable at runtime. So if the error does occur, there should be some code path that ensures that the application keeps going. There's not going to be a crash or a restart. How do we propagate these? we use sealed class hierarchy. So we have some custom class, which is sealed, representing the result of the function, in this case, my function result. And we have some subtypes that represent the different scenarios that can occur when you call that function. So if it's a success, then we have a myFunctionResult.success class, and then maybe we have some missing requirement error. What does the user expect? They expect that they can handle all of the error cases and that they should handle all of the error cases. And they expect that they can use a when statement so that the compiler will make sure that they do cover all of those use cases. Let's look at some example code for this. This is actually slightly modified from our real API, but we have a class geodatabase. And this geodatabase can commit transactions, so you can have a bunch of adds and then commit them all at once. Now, this function can fail if, for example, the transaction hasn't been started. So by default, this would just throw an exception. Instead, we can create a sealed class called commitTransactionResult. And then if it was a success, we can return an object success. If it was a failure because the transaction wasn't started, then we can have an object representing that case. And maybe later on down the road, we say, oh, actually, we are going to get an exception thrown if the geodatabase is closed. So we can actually just have a return type for that as well. That way, we don't have to throw any exceptions. Now, I just want to note as well, these can be classes. These can be classes with properties inside of them. So you can give more information to your users in the specific error scenarios where it's relevant. We can return that from the function. And then the user can look at the transaction result and use a when statement to write specific code to handle each scenario that may have occurred when they tried to commit that transaction. And what's really nice about this is that if it was a not started failure, then they can have specific code to handle that case. And if it was a geodatabase closed error, then they can have a specific scenario, specific code to handle that scenario. So each error has its own function to handle it. Okay, the last type of error that we have are lenient errors. These are unspecific at implementation time, meaning that it's not really important to know how or why the error occurred. But they are recoverable at runtime, so if it does happen, we still want the code to be recovering from that. We want there to be a happy code path for that. And why are they unspecific? Well, maybe there's only one error case, or maybe it's just not important to know any information about the error in order to recover from it. How do we propagate these? We use return types again. So if you have a normal object being returned from your function, you can use a nullable return type to signify that some error occurred. If we have a unit type, then we can use a Boolean return where success is represented by true and failure is represented by false. And the user may or may not end up using that Boolean. And for collection types, we can just return an empty collection. So so we actually renamed the functions in our API as well, just to be extra explicit about these potential failures. So for the nullable return types, we added or null to the end of it. And for the other types, we added try to the beginning. And that just signifies to the user, hey, when you call this function, something may go wrong, and you should know about it. What does the user expect? They expect that they don't need that specific error information in order to recover from it. And they expect that they can write code where the flow of the code continues as normal as part of processing the return value. So if we return a nullable, they can use the safe check operator or the safe call operator to make sure that when they process the value, it will only happen if an error didn't occur. They can use an if statement to check if the Boolean return was a success. And if they're if they get a collection return type, then they might be iterating over it. And then that lambda that gets called will only occur if there's actually something inside that collection. So if there was an error, it's fine. The code just won't run for that type, and everything's happy. Here's an example from our API for a lenient error. So we have a coordinate formatter class, which has a function from latitude or longitude. This takes some string coordinates, which need to be in a specific notation. And if they're not in that specific notation, then by default, this is going to throw. Right, so the user is trying to create a position. This function returns a point, by the way. So the user is going to try to create a position from this function. They're going to pass in some invalid string for the latitude, longitude, and it's going to crash. So what do? We can just return a nullable point instead of just a point, and then we catch the exception. We return a nullable, null in that case, And the user can now see, oh, okay, this position might be null. Well, I'm only going to move my camera to that position if it's not null. So it's really easy for them to handle that scenario. And then to be extra explicit, we also add or null to the end of the function name. And to be extra explicit, we also add to the documentation, hey, this can return null, including when the given string cannot be interpreted. So in summary, those are the 3 types of errors. You have logic errors, which throw. You have domain-specific and lenient errors that are recoverable. The code is able to recover from those cases. And we have specific errors where it matters what the error was that occurred, which covers the logic and domain-specific errors. And I'll have this, this chart up again at the end of the presentation. All right, so now let's talk a little bit about our experience designing an SDK and designing for error. So how do we approach the error propagation? So a little bit more background on our SDK. We actually build everything on top of a C++ core. This is where the actual implementation of the business logic is done. And on top of that, we have a C API and some platform interop code, which in our case is JNI. And on top of that, we have our actual Kotlin API, which calls down into those things and exposes it out to our users. And also important to note, the JNI can throw. So that's how we receive the errors from down below. We have a giant code base. We have about 2,000 functions. This year, we were able to redesign the API, specifically that Kotlin layer. So previously, we were with the Java team. Everything was written in Java, and we, because of interop, you were able to use Kotlin. But now we were trying to actually use Kotlin patterns, and we had about a year to expose it. And we also had some specific constraints, so we have to avoid breaking changes. If we release a new version and our users want to upgrade to that version, we need to make sure that their code doesn't break when they do that. We have a constantly changing C++ core, so that's written by a different team, and they can make changes to it at any time, and we really need to be reactive and adaptive to those changes. And as much as possible, we actually tried to generate our API automatically. So we have some YAML files that describe the API for all of the platforms that we support, and then we generate Kotlin code based on those files, and then we audit and modify them manually where we need to. So for each of the errors that we have, actually by default, all of our errors are exposed as logic errors. So if the C API throws, then we just throw an exception in that case. And that's our default case. But for the other scenarios, we actually had to go through, review all of the functions that we have, and identify whether, for example, they should be lenient errors. And if we found that they should be lenient errors, their use cases really supported leniency, then we refactored them as I described previously. We changed the return type, and we renamed those functions. For domain-specific errors, we had a little bit more trouble. So we reviewed all of those cases. We identified any errors that should be domain-specific. And then we found that our constraints had a bit of an obstacle for us, because the C++ core could introduce new ways for errors to occur at any time. And we have a constraint against breaking changes. So let's say, for example, that commit transaction. Actually, in our API, there is not an exception that occurs if the geodatabase is closed already. But we can imagine that the C++ team could decide, oh, actually, we need to throw an exception in that case. And they could do that at any time for a future update. So if we had a sealed class that had all of those specific error scenarios encapsulated as classes, as subtypes, then our users would upgrade. They would have a win statement handling the error cases, and they would discover, oh, I'm missing a type. The compiler's not letting me compile my app. So that would be a big problem for us. What did we do instead? We decided to use results. So this lets us propagate exceptions in the return type of the function. It's less explicit than sealed class hierarchies, and it's not generally recommended for domain-specific errors. But we found that it fits our use case really well. We can still let our users recover from cases where an error occurred, and we can give them extra information in the form of the exception if an error does occur. So we still are able to have a clear and communicative API while allowing recoverability. All right, so just to tie things up, let's talk a little bit about suspend functions, properties, and constructors. They could probably be a whole talk of their own. So suspend functions, generally speaking, you can treat them as normal errors. So a suspend function can throw, it can return a nullable, it can return a sealed class hierarchy. In our case, almost 100% of our suspend functions are I/O related, and so because I/O exceptions are kind of like domain-specific errors, and they generally should be treated as lenient, we do end up returning a result for those as well most of the time. But what's important to note here is if you are catching exceptions from your inside of your suspend functions, you need to make sure that you don't catch cancellation exceptions, because then you'll just completely destroy structured concurrency. Properties should represent a state, not a behavior, according to effective Kotlin. I agree with that. So users don't generally expect properties to throw exceptions, and so we don't, and I don't recommend that you do it either. And constructors can actually propagate logic errors by throwing, but in the cases that other error scenarios were needed for us, we actually decided to make those constructors internal or private and expose a factory function so that we could still return something different if necessary. If you want to do some further research on error handling, there's some articles here. Roman Elizarov has a really great article on Kotlin exceptions. I found the result keep was really helpful. They have a great section on error handling. And then effective Kotlin is always a great resource to go back to. OK, here's that chart again for the different error types. And I have a bunch of QR codes on the next slide because I just saw in the last talk that there was some nice website where you could share your slides. So I've put that up now. Cool. Thanks for coming. Any questions? If not, you can always come talk to me after. And thanks for coming.